Hello bro. Today we're going to do advanced recursion, and you can find the video on my channel where I was explaining a beginner tutorial for beginners with recursions, but today I will do a slightly more advanced version of it, and this version will include so-called encoding, Shannon-Fano encoding, and you can find information on it in the internet. But I will obviously explain how it works and why is it good to use recursions in the solution to the following code, and we'll go all the way through it. So let me start from Shannon encoding and what's the input, what's the output we want to get. And the idea behind the Shannon-Fano encoding is that we are getting frequencies of words out of some text. So this is obviously just artificial example, but in the real life you would have a text and you will just analyze how frequent each word is there, and then you will kind of normalize it, right? So the probabilities are given here. As you can see, for this artificial text that it should have been analyzed before. We have a probability of the, or rather frequency of the 0.5, and he is 0.3, she is 0.1, it's 0.1. And so each word when the tunnel would be reading through this text, with the kind of stupid text, of course it only consists of only 4 words. That's not a real example, but still the probability of getting a day in this text would be 0.5, getting a he 0.3, she 0.1, and it 0.1. And based on this information that we got about the frequencies and probabilities, we would like to find efficient encoding for the following words. What's encoding is? It's basically a representation of this word created in a binary, so it might be. So this is one possible encoding we could do, and then let me do this. So this is one possible encoding we could do, or we can also do the same one but with the 0 at the end. It will also give us a possible encoding. So as you can see, this is a representation of the in binary, but the encoding we choose ourselves. So it could be 0010101100. The only crucial thing is that this encoding has to be unique for each word. So for example, if we for the following encoding, if you get a string that looks like this, we can see that just looking at the start of it and producing it from the start, we can see a 00 here, and we already know that it is there. The word is there, and it cannot be anything else because after it goes 0, it goes 1. So 001 is absent here. We cannot get any word from it. So we know that 00 is obviously already a word there. And then we go to the next one. The next one is 10. It starts from 10. We look at our possible encodings, and we see that 10 is only possible word from here, because after that it goes 101, and 101 is absent here also. So we know this is a word. And we go, so on we go, and here we see another word here. It's it, and then at the end we see a she. So the thing is that if I would do the encoding something like this, now we have a problem. Why? Because here we see a 0 at the start, and we see a second 0 at the start. And we don't know which word we have tried to encode here, which word was encoded here, because 1 0 represents a he and 2 zeros represents a the. So we cannot unambiguously decode what is written here into zeros, right? Because 2 zeros can mean the, or 2 zeros can mean he, double he, sorry, like this. And we cannot decode it correctly. We have to decide somehow, and this is what we want to get rid of. So we want a completely clear understanding of what encoding means. Alright, so how does Shannon-Fano encoding works? I'll explain it here. How does it work? So it takes our input, we have our input of those 4 words, can be more, it doesn't really matter the amount, can be much more, and usually it will be much more, because it's kind of stupid to have text that consists only out of 4 words, right? So we have our input, and we have some kind of starting point here, and we can see that probability of getting either of these 4 words is 1, right? So it just sum up 0.5 plus 0.3 plus the rest of it is 1. So what we would like to do now here is to find the most efficient split here. What's the efficient split? The efficient split would be ideally where the probability of getting either of those is divided by 2. So basically 1 divided by 2 is equals to 0.5, obviously. And we want to split those 4 words into 2 objects, where into 2 different dictionaries, kind of, where probability of getting each of those dictionaries is 0.5. So this example is quite easy, and we can already see that the has a probability of 0.5, right? So we can simply put the here, and then what we are left with the rest of it. Let me copy it here. So we can obviously see that he, she, it. Probability of getting he or she or it is 0.5. And now we mark our nodes. So on the left we put 0, and here we'll put 1. You'll see later what does it mean. But just remember that on left we put 0, on right we put 1. And then what we would like to do is basically repeat the same process. So this is already gives you a kind of intention that will gonna be nice to use recursion here, because just as we had with factorial, we repeat the same steps. So let's see what we get here. So we got 0.5. Ideal split would be 0.25, right, on each of those nodes. But unfortunately we cannot reach 0.25 here, because we have one word to 0.3, and the rest of those are 0.1 plus 0.1, so 0.2. So obviously, I mean, that's maybe not obviously, but still quite easy to see that the next split would be we put 0.3 on the left and the rest on the right, or we can alternate it, doesn't really matter. So we put she and then it here. And this can be got with probably 0.3, and this is 0.2. And again we do same thing with putting 0 and 1 here. And for she and it we see that the best split would be 0.1, again by dividing by 2. And obviously the best split can be reached here, because she and it are both the same probabilities, 0.1, so we just do same thing as before. It doesn't really matter where you put the she or when do you put it, but you still put 0 and 1 here. Okay, awesome. So we have done this process of Shannon coding, And what we can see now is if we take a word and we want to find encoding for this, we simply look through our tree, so our binary tree, where what we got, and we look where there is in this tree. There is located here, so we start from our starting point, and we see what path can we take to reach there. So the path that we should take is basically quite easy. We just go left, right, go left, and that's it. And we write what we saw during taking this path. So we saw the 0, and we simply write 0 here. Then we would like to find an encoding for he out of this tree. This is slightly harder, but not hard at all anyway. So we see he is here, and we take a right and then left. And during this process we have seen 1 and 0. So we simply write 1 and 0 here. Amazing. And we repeat this process for the rest of the words. So quickly do it. So she is located here. So we should take right, and then left, and give us 1, 1, 0. And the rest one is it, give us 1, 1, 1. Amazing. So that's an output that we would like to get from our Shannon encoding. So our desired output will look like this, as you already saw from my example. This is one of the possible encodings. I mean, here it's also possible to change it and she to basically switch them, and then the encoding for she would be 1, 1, 1, and the encoding for it would be 1, 1, 0, but it doesn't really matter. And so this is a desired output. So we have such an interesting algorithm, and obviously we don't want to do this by hands every time we see a new text, so we want to code a function for this, right? So let's see how we can do this. I will call it Shannon-Fano. And so what our function takes an input, takes a dictionary, so I'll call it data of type dictionary. And what do we want in the output? It's also dictionary. So I'll just mark it here like this, and we basically created a function with an input and output. So at the end we want to return a dictionary with encoded values, right? And so what we'll start from is the kind of preprocess for our dictionary, because dictionary is a little bit hard to work with, as we cannot iterate through it, and you also cannot sort it. This is a slight problem I encountered while solving this exercise. And what we would like to do at first, to instead of having a dictionary, I would like to have a list of tuples. So it will look exactly like this, 0.5, and then he 0.3, and so on and so forth. I'll not write all of them, but still you can see that it looks a little bit different, but still the information is not lost. So we have a list of tuples. How do we convert a dictionary to a list of tuples? I'll call it tupes, and we do it the following way. So this is a syntactic sugar that I will use here, but I will explain it, so no, don't be scared of it. It's fine to use it, and I encourage you to use it as well. So our tubes will look as follows. We have a key and a value in the tuple, and we do it for key value in data items. So what we're doing here is basically items method returns us a key and a value for each item in the dictionary, and then we simply put them in the tuple key and value, and the following part of code gives us a type of generator, and we want to put everything in the list, so we simply put square brackets here and here, and we are getting a list out of it. And the default implementation of list allows to put a type of generator inside, so that's why we can simply get our tuples inside of a list here. We can try to do it here, return the troops, and just to, of course, it doesn't return dictionary right now. Let us see how it will look like. So print Shannon-Fano test input. Okay, that's a little bit strange because I've done something before. Sorry for this, but this is what we see here. It's basically just what we have expected. We have a list of tuples, and then what we would like to do is, obviously we don't want to return them. The first thing we want to do with them is to sort them. You understand why it is important later, but I'll sort them with I'll sort them such that 0.5 is the greatest value is we take the value of probability, and we sort it by it as a key. That's why we will have to pass an argument of key, and here we pass a lambda function that will do the following thing. Basically, oops, it should be on. So it basically just takes only a value and sorts our whole list with respect to this value. And then we want to have a yeah, let's look at what we'll get. The output will be different because now we sorted it from in ascending order, so basically from the least value to the greatest, and we want descending order. That's why we put reverse equals true. Amazing. So we've got what we wanted, and obviously it was the same before, but only because I put the values in the right order. If they would be changed, then we would need a sort. Amazing. So now we can actually go and start the encoding. I'll create a different function for this. I'll call it encode, and this function will obviously pass our tuples. Let's write this function. You have I'll call it left words. Left doesn't mean direction, it's just rather the words that are left to be encoded. That's what it means. And left words will be a part of type list, and then we'll need also a string, but I'll explain it later. I'll keep it like this for now, just for easier understanding. Okay, amazing. So we have to right now actually create a recursion here. So what do we need for recursion? An actual recursion and a base case. Base case I will leave for later. I'll comment it like this so we don't forget about it. And now we have to think how our recursion will work. So based on what we did here, what we have done here, you can see that in each iteration what we do is we take the sum of all probabilities of the words that are left. So here it was 1, and here it was 0.5, and so we basically take this probability, then divide by 2, and then we try to find the most efficient split based on it. So what I'll do is basically the same thing, and I'll find the split value. It will look like this. So basically, I'll just take all the probabilities and sum them up, and that's it. But we also divide them by 2. I'll leave it for later. Okay, so what we need, x. And we can try to look at what we are doing right now, so it is a little easier. So we can see that now we got a sum of all probabilities. This is also a little bit of syntactic sugar. It's very similar to the thing that I have written here. It's simply that's like a small version of for loop. Instead of writing the whole for loop, we do generate the generator, and this generator only takes values of takes second values of each tuple that we have in the list of left words, and then we put it in the list, and then we simply take a sum of it, and sum is just a base function. It just sums all the values in the list. So we got a 0 or 1.0 at the end. This is correct, obviously, but for split value we want to half it, right? Because the most efficient split is half on each side. So we just put a divide by 2 here, right? Easy. And we get a 0.5. Amazing. So what we would like to do next is, now we actually want to iterate over this list of left words, and we want to find a word where we will split, and where part of it will go to the left and part of it will go to the right. In order to do this, we will need a variable called current sum. It will be equal to 0 at the start of iteration. So basically what will be, let me quickly erase something from here. This is useless. So what we'll be doing is we'll be looking at we'll be summing the values of probabilities until we get the point of where split value is the same as our current sum. So we go from left to right, we look at the probability of that. It will be at the very first iteration, we'll look at this probability. So we get a 0.5, we add it to current sum, and then we'll compare it with split value. If this is greater than equal to a split value. And if it is, we'll do a split. You can already guess that this split will include some recursion. Okay, let's see. So we'll need an index. We'll need it for later, but you'll see where it is important. In enumerate is also a function in Python. It also basically gives you an index of each element that you are iterating of. If you don't do anything, if you don't traverse your array or do anything with it. So that is exactly what we are doing here. We are just doing enumerate of left words, and the first thing we want to do is obviously add the value of the first probability here. And then we would like to compare actually if our current sum is greater or equal to the split value. And of course, if it's not, we just go and sum another element, so it would be plus 0.3 here, but obviously we're not doing it because we have already reached our split value. So what we are doing instead is we would like to do this split, and we are doing it by basically a recursion. I will do a left node. A node is basically a part of tree. This is called a node, this is also called a node. And what we are doing here is we calling the same function encode. And we want to encode the same left words, but we only take we only take values from the first value to the last value, but we need a +1 here because enumeration here starts from 1 and I +1 is exclusively taken, so that's exactly will give us I here. And what we are still missing here in our encode function is this 0 or 1 that is being somehow have to be memorized by the algorithm such that in the end we will get all the encodings correctly. In order to do this, we will need another parameter in our function. It will be an empty string here, and here I'll call the start of type string. What we would like to do here is basically pass this string, but with the value of it, and we'll add a 0 at the end. So what we're doing here is basically we're taking everything that was before. So for example, here if we would go in left from he/she to left to he, we take everything that was before and we add a 0 at the end. This is exactly what we are doing in our recursion. And then we do the same thing for right node. The code will be slightly different. Code right word. Oops. Left words, and then we want to start from I +1 and we go up to the end, but to the start we only add a 1 here. Amazing. So, and at the end of all of this we want to simply return. This is also a syntactic shortcut, just don't overwhelm yourself. This small code basically merges two dictionaries into one. So just don't think about it that much. It works like this. Okay, amazing. We're almost done. So we're still missing a base case, and also we're missing a slide thing here. And this slide thing will be such that it might happen that we won't find all the our split into in all the words that we have done here, in all the probabilities. For example, a nice example would be at the end. So at the end right here, we would have our left words will only be in our left words. We'll only see she and it at the end, and our algorithm will be comparing. Okay, no, this will work actually. Never mind. Let's just do a base case. So what a base case will look like? Our base case will simply be handling if our array somehow would have a length of 0. I actually don't know if it's possible or not, but I just rather like to make everything clear. So if len of our left words is less or equal to 0, then we just return an empty dictionary. Easy. And if length of left words is 1, then we want to return a new dictionary where a key will be our only one word, and you have to be careful here because leftwards is still a list, and in the list we take a first tuple, and the only tuple is there, and then in this tuple we take a first element. And this is our key, so this will be exactly our the value. Or he, she, it, one of those. And then what we are doing next, we put in a value, and the value will be simply a start. So string we've got so far. We don't add anything here because we have only one left word, so we just add it here. And I think we are done. Let's test what we have done here. Yeah, I have to do this and share this. You can see our encoding that we've got from here. And you can see that output here and here is the same. So that's it. Let me know in the comments if what you think about it, if everything was clear or not. And hope it helps you to understand recursions. See you, bro.